Hi, my name is Bo Yoon, and I'm a master's student studying data science at SMU. Today, I'm going to walk you through long short-term memory, which is a type of recurrent neural network that has been gaining traction for sequential data. First of all, what is recurrent neural network? In a traditional forward-feeding neural network, we assume that all inputs are independent of each other. But what if the data is dependent and sequential? RNN is a type of neural net to recognize patterns for sequential data, such as text, genome, and handwriting. Due to its internal memory, it is perfectly suited for machine learning problems that involve sequential data that are dependent with each other. Let's work through a very simple example. Let's say that David works out in the sequence of chest, shoulder, and abs, one workout a day, regardless of what day it is. So Monday he does chest, Tuesday shoulder, Wednesday abs, and Thursday back to chest. For a typical feed-forward net, we will use a different features such as day of the week, month of the week, and the health condition of the day as inputs, and a complicated voting system to predict what the next workout will be, but the result won't be as accurate as what we can simply get from the predefined sequence of workouts. Here, when we are using RNN, we simply input what workout we did yesterday, and the prediction naturally goes to the next predefined workout sequence. However, let's say something came up and you couldn't work out and had to skip a day. Then we go one time back and make a prediction based off the workouts on the day before yesterday and make subsequent predictions after. This is a simplified version. New information is fed into the prediction along with predictions made for the previous time step. And this process gets repeated. Okay, now we understand the big picture. Let's take a look at what's happening under the hood. Let's talk about math. At time equals 0, x0 is fed into the first equation to get HO. Here, in the middle term, equals 0 because the time becomes negative. Once we get HO, then we plug it into the second equation, multiply by the weight WY, and plus the bias term. We now move on to the next x1 node, and we can use HO from the previous run to calculate H1. This entire process is repeated until we reach the final YI prediction. Okay, sounds great. But what's the problem with training RNN? RNN is mostly used in sequential data that has time steps. Let's say we have n number of layers. Then we need to backpropagate so many layers, and this leads to vanishing gradient problem. Okay, so let's see how the problem arises. Each layer comes with a cross entropy loss, and its gradient is represented by E as shown on top of each layer here. In order to calculate these gradients, we use backpropagation through time, and we need to sum up gradients at each time step as represented by WR that are located between layers. The term in the red box is continuously multiplied across multiple time steps. Since we're using sigmoid function here, which means the term in the red box is less than 1, and when this term being multiplied so many times, the value will get close to 0. Then rho E2 over rho W gradient will quickly vanish over time, and long dependencies in the earlier times will not contribute to the later times at all. But what if we use a linear function instead of sigmoid function? Well, in this case, the weights are high, which then leads to exploding gradient problem. In that case, the resulting vector will show up as NAN during implementation. One solution is to use gradient clipping, which is capping the gradient at a certain number so that it doesn't go over it. Yet, there is a better solution. Solution to mitigate vanishing or exploding gradient is to use long short-term memory. We replace each hidden layer with LSTM cell. We also add cell state as represented by C that connects to the next sequence of the network. So now let's take a look at this high-level view of how each LSTM cell works. Each LSTM cell maintains a cell state vector, also known as long memory. This purple box is the cell state, and the LSTM cell that is in the next time step can read from it, write to it, and reset it using explicit gate mechanisms. Cell state runs from one layer to layers down the sequence with very minor linear interactions. There are 3 gate mechanisms that consist of short-term memory. Input gate controls whether the memory cell is updated. Forget gate controls whether the memory cell is reset. The output gate controls whether the current information is visible. Let's start with the forget gate. It's important to identify which information is not needed and need to be thrown away. The forget gate is a sigmoid layer that implements this task. And the output of this will be either 0, which means discard the information, or 1, which means keep the information. In the previous step at the forget gate, we decided which information to keep or discard. Here at the input gate, we're going to decide which information we'll store. We have 2 parts, sigmoid layer, which is the input gate that decides which values will be updated. And we also have 10H layer that creates a vector of new candidate values that could be added to the state. And then we multiply these 2 outputs and pass it to the next state. Here in the cell state, we multiply the old cell state by ft in order to forget things that we need to forget. Then we need to input gate it multiplied by ct, which is the new candidate values, and they are scaled by how much we decided to update each state value. Now we run into another sigmoid layer to determine what part of the cell state we're going to output. Then we push the new cell state through 10H and multiply it by the output of the sigmoid gate. Okay, so here we're going to go over how LSTM stores and updates keywords through an example sentence that has long dependencies. David loves to play around data and draw insights from data every day. No wonder he's such an amazing data scientist. His brother Kevin loves to paint every day. Kevin will be a great painter one day. Okay, so here we have 2 clearly separate sentences here. The black arrow that passes through the sentence here identifies and stores keywords in the cell state, otherwise known as the long-term memory. In the first sentence, it'll pick up the word data, which leads to David being a data scientist, and store it until it runs into the word paint, which leads to his brother Kevin being a painter. So CT1 minus 1 is the memory of the word data, and the current word, which is paint, is passed on to the sigmoid function, which restricts the output vector to either 0 or 1, depending on whether it decides to discard the information or not. So here, when the output vector of 0 meets the vector that has the word data, the multiplication will result in 0, and in turn, forget the word data. So not only we forget the previous memory, we also have to update the input, and we'll use the sigmoid and 10H function. For the 10H function, we're assigning certain weights to ht-1 and xt, add the bias term, and then push them through the 10H function. Next step, we multiply the output from the input gate and from 10H, and that's how we add the new memory for paint. Okay, so output gate. Here again, we apply weights to hidden layer of ht-1 and xt, and then push them through the third sigmoid function. We take the newly added memory from the cell state, apply 10H, and then multiply with the output from the sigmoid function. Then we finally get the hidden layer, HT, and YT of the current state. Okay, now let's walk through an example on how to set up LSTM network on Python Notebook. The data is movie review with a mixture of positive and negative sentiments. First, we're going to import Keras packages. And then we see here this different parameters. We embed theme, LSTM out, batch size, dropout X. These are the variables for hyperparameters, and their values are somehow intuitive, but should be played with in order to achieve good results. Please also note that I'm using softmax as the activation function. The reason being that our network is using categorical cross entropy, and softmax is just the right activation method for that. Here, we're going to separate the train and test data set. And then here we are training the neural network. We should run much more than seven epoch, but we'd have to wait forever for this to run. So let's do 7 for now. Also here, we are extracting a validation set and a measuring score and accuracy. Once that's done, we're finally measuring the number of correct guesses. It is clear that finding positive sentiment goes very well for the network, but deciding whether it is negative is not really, as seen here. My educated guess here is that the negative training set is dramatically smaller than the positive, so the bad results for the negative reviews. Okay, to sum it up, when dealing with sequential data, long short-term memory is robust against the problems of long-term dependencies. There are 3 key gate mechanisms in each LSTM cell that play important roles in solving long-term dependencies, which are forget, input, and output gates. That concludes my presentation. Thank you for watching the video. If you have any questions, feel free to email me or connect with me on Discord.